is Dr. S.P. Arsaf from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are mainly discussing about the principles of active vibration control. So, in the last module, we discussed all conceptual feature and even that what the design features are there, how we can exactly go for control of vibration using the passive vibration control. And we know that there are certain limitations and there are certain good points, and according to the system application we can adopt the passive vibration control. But now you see here with the recent trend, and you see when the sophisticated arrangements are there and according to the application and environment, we need to go with the active vibration control, which is the second mode of vibration control. So, in last lecture we discussed about the basic features of the active vibration control, in which we know that whatever the primary source through which the excitation is occurring in the main system, we can simply by putting the secondary source, a negative force can be generated, and that can be, we can say, the counterbalance force is there. And in this particular mechanism there are three main devices which can straightaway put to find out the desired properties. Like first the sensor, when any force, voltage or anything is being or the stress when it is being acted on the system, the sensor which can sense any dynamic parameter or anything you see which is being happen to the system, simply sensing the part. So, first part which is to be required is the sensor, and then you see here the other part is the actuation, just to actuate the system against the excitation force. So, actuator is now generating the force which can balance whatever the vibration is being the vibrating features are there with the system. But this sensor and actuator is coupled with the, we can say, the control unit. So, this automatic control unit, or we can say it is being basically we can say featured with the analog or this digital control system. It has to balance in which you see if amplifier is required or anything is required, it has to pass through, and we can say a magnified force can be generated through the exciter, or we can say actuator. So, this is one way to control the vibration using this active vibration phenomena. But sometimes you see here, even to put the micro sensors or even the sensor and actuator and then the entire control unit is not the robust sophisticated system. Then certain the similar kind of application, if we can generate or if we can combine using the material known as the smart material, then you see here the purpose will be solved using for a vibration suppression using this active vibration. So, we are saying that when the we can say the intelligent or the smart materials which can be framed in such a way that we can get that various categories are there under that, like the shape memory alloys and the shape memory functions. In that you see that how ingredients are there in the shape memory alloy material in which such actions can be happen. Second, the rheological fluid, either based on the magnetorheological fluid or electrorheological fluids, even magneto-restrictive fluids, and the last but not least the vast category of the piezoelectric materials. Right from Madame Curie and the Pierre Curie, they generate this in somewhere in early 90s or even the 18th century, 1880s, that some of the material can even generate the force when any mechanical part is being applied, or due to the electrical voltage is changing, or the force, when the force is being applied, there is a change in the electric voltage across the material. So, all these materials which can sense and automatically which can actuate as per the requirement are known as the smart materials. So, in today's lecture we are going to discuss about one broader category of the smart materials is the piezoelectric materials in the conceptual features. So, the piezoelectric materials are the materials that produce a voltage when the force or the stress is being applied and the actuation is being happen due to that. And since this effect also applies in the reverse manner, that means you see when the voltage across the sample will change, and you see when it is being applied, the stress within the sample can be produced or induced because of the resistance. So, you see here in the vice versa concept, whatever the requirement is there, these materials can provide immediately the required actions. The word piezo is a Greek word that means, you see here, to press, and whenever this pressing action is there, the required features are being coming out. Therefore, piezoelectricity means the electricity generated from the pressure variation or any kind of, you see, the intensity of these forces. And that is why you see a very logical name is coming out from that piezoelectric materials. And you see, once a suitably designed structure which is made from these materials can therefore be made that the bend or expand or contract is any action is being happening, a voltage is being coming out from that, or when the voltage is being applied, then all these actions, the bending, the expanding or the contraction can be happen to the systems. So, that means you see here, whenever you see the pressing actions are there, electricity is generating in that. So, piezoelectric effect, if you are just going some back history, it was basically discovered by Parry and the Jacques Curie, which they named by that, you see, you know, like the Nobel Prizes to both of them separately. And you see here, they simply demonstrate that when a stress field is being created or being the entire force field is being applied to a certain crystalline material, at that time it was a crystalline material, an electrical change was produced on the material surface. So, that was the basic invention made by these Curies. And it was subsequently demonstrated that the converse effect is also true when an electric field is applied to these materials, the crystalline materials, then there is a change in its shape or the size, which we are saying that the piezoelectric materials. So, this effect was found to be due to the electrical dipoles of the material and spontaneously aligning in the electric field. And because of this alignment, there is a clear change in the shape and size according to the intensity of these field features or the dipole moment features. So, when we are just trying to look at the basic feature, then we will find that there are two main things. One, due to internal stiffness of the material, the piezoelectric elements, they are also found to generate relatively large forces when their natural expansion was constrained. So, that means this observation ultimately lead their use as actuator, because we know that whenever the internal stiffnesses are being, you know, like just affected by this by these, you know, like we can say whatever the forces, whatever the voltage changes are there, the large amount of the reactive forces are being coming out. So, that means you can actuate the entire material by just changing their internal stiffnesses. So, you see these piezoelectric materials can be acted as an actuator part, and at the same time, if the electrodes were attached to the material and whatever the charge generated by the straining, whatever the force which we are applying there or the pressure or the stress, the straining the material could be collected and then measured. So, we can say that the piezoelectric material can also be used as the sensor to measure the structural motion by directly attaching them to the structure. So, you can see that because of the internal inherent property, the stiffness, which is nothing but you see, you know, like just measuring whatever the force per unit deformation, because of this, like whatever the variations are there in stiffness, these materials are generating large forces when their natural expansion, you know, like because of the stiffness variation is being constrained, and because of that constraint feature is there, the forces which are being coming out, the actuation feature is there from that, and the same time whatever the molecular motions are there, they can sense because of the change in their whatever the, you know, like the electrode features and the strain features are being there associated with that. So, we can say that the piezoelectric material can be acted as a sensor and can also be used as the actuator part. So, most contemporary application of the piezoelectric use is the polycrystalline ceramics. These materials have a lots of applications instead of, we can say, the naturally occurred the piezoelectric crystals. So, the piezoelectric materials can be categorized into two main broader categories, which we are going to discuss. One, the naturally occurred the piezoelectric feature, or man-made piezoelectric materials. So, the ceramic materials which can afford the number of applications, they have lots of we can say advantages, like they are hard, they are also dense and can be manufactured up to, we can say, almost any size or the shape according to the applications, and they can provide a sufficient amount of the piezoelectric effect because they have the polycrystalline ceramic material inside that. So, piezoelectric transducers have lots of applications, especially when we are using these piezoelectric material as the vibration controllers. So, these transducers can be used as the sensor and the actuator in the structural vibration control system, and they can provide a sophisticated and you see here the excellent applications towards the sensing and the actuating feature, and their accuracy is also of a high level. So, the Curie family, whatever they discovered based on they discovered simply a class of material that when the pressurized generate electrical charge, and when they placed inside the electrical field strain mechanically. So, this is the concise way of we can represent the piezoelectric feature of the material. So, piezoelectricity when linearly, which we just want to define linearly, that means the electricity generate from the pressure, and you see here various materials like the monocrystalline materials as the quartz, the tourmaline, topaz and the rochelle salts. You see there are four. One is the quartz, then we can say that the tourmaline, the topaz and the rochelle salt, they are the naturally occurred monocrystalline materials, and they can generate the electricity just by applying the pressure or any kind of force application. So, these are the naturally occurred piezoelectric feature piezoelectric material, and the ability of these piezoelectric materials to transform mechanical energy into electric energy or vice versa was mainly discussed by these Curie family, the Pierre Curie and Jacques Curie. But sometimes you see here, when we are applying these materials, they are not absolutely actuating in whatever the required force is. I am talking about the naturally occurred material. So, we need to go with the man-made piezoelectric material which can be used as the sensor and actuator together, like the polycrystalline ceramic material as I told you, and one of the best feature in this is the lead zirconate titanium, and this lead means P, zirconium Z and titanium T. So, PZT, which is a very common you see in this piezoelectric material, the PZT can be processed to exhibit the significant piezoelectric properties in that. So, this is the man-made polycrystalline ceramic material in which all three materials, the lead, the zirconite and the titanate they are simply exhibiting excellent features which is being required to sense and the actuation feature in this material. So, PZT ceramics, which we are saying that it is the category of this polycrystalline ceramic material. So, PZT ceramics are relatively easy to produce, is in manufacturing point of view, and can also exhibit the strong coupling between the mechanical and electrical domains when we are just trying to change mechanical energy to electrical energy or electrical voltage into the mechanical strain. So, that is why you see the PZT patches are having excellent applications wherever it is being required in that. and this enables them to produce comparatively large forces, or we can say the displacement, especially in terms of the actuation feature or in terms of the sensor feature, from relatively small applied voltage, or even for relatively large the small forces or the displacement, they can even produce the large voltage together. So either of side you see here, these PZT patches can exhibit excellent features there, and they are the most widely utilized material in the manufacturing of the piezoelectric transducers for vibration control under the active vibration category. So the high modulus of elasticity, when we are just looking from the mechanical point of view, under the elastic nature, they have excellent modulus of elasticity as compared to the material, even they can go beyond that limit. And even though piezoelectric sensors are electromechanical systems which can react on compression, the sensing element is almost showing the zero deflection in it. So that is an excellent feature you see here, that even since they are electromechanical systems, so their reaction against that is really a stable part. And this is the reason why the piezoelectric sensors are so rugged, and they have an extremely, we can say, high natural frequency, and they have an excellent linearity over a wide amplitude range of the excitations. So when we are talking from the vibration point of view and we want to control the excitations, and they have these piezoelectric materials or the sensors, means from sensor point of view, they have high natural frequency, and the same time they are showing their linear feature or the large amplitude part. So the vibration in which you see, since the vibration is featured out by the exciting frequency and the amplitude, they are showing an excellent character from both the point of view. And along with that, the piezoelectric technology is insensitive to electromagnetic fields or the radiations, and that is why you see here with these two features, since they are insensitive against these, we can say the environmental features or whatever, like the outside part, it is enabling in the measurement or Hertz conditions for the application of these piezoelectric sensors. So that is one of the unique feature you see here, that they can be applied to any kind of conditions, and they are insensitive to that outside conditions, is whether it is working in the electromagnetic field or whether it is the radiations are there all outside. Some of the material, like we can say the gallium phosphate or the tourmaline, have an excellent, we can say, stability even over the temperature range of 1000 degrees Celsius. So we can say that with this piezo actuation and the sensing feature, even they can be applied to any severe conditions, outside condition, and even the temperature ranges. These are the common advantages which enable them to use in many of the applications against any kind of environmental features, irrespective of whatever you see, the changes are there, the drastic changes are there, the cyclic changes are there in their environmental features. But one of the disadvantages of these piezoelectric sensors is that they cannot be used for true static measurement, because a static force will result in a fixed amount of charges on the piezoelectric material. So that is one of the drawbacks that you see whenever we are going for the static measurement, whatever the oscillation features are there with the charges, they are absolutely not showing the clear variation. So we cannot say that what exactly changes, because the static means you see even the force has a constant magnitude, and whatever the constant features are there, that cannot be accurately featured out from these materials. But whenever we are talking about the dynamic feature, like in the vibration or any other where the motions are being a clear part, this is one of the specific material where we can straightway apply it and get the desired results. So we can go with the basic characteristics of these sensing materials. Like you see here, we are categorizing, say, based on the 4 principles. First, the piezoelectric. When we are using the piezoelectric material, their strain sensitivity, as the voltage changes are there corresponding, is very excellent. The threshold value at that is very low, and the span of this threshold ratio is very high because of this piezoelectric action. And if you are using the piezoresistive feature in these materials, sensing material, their strain sensitivity is quite low, very low as compared to the other things. Even their threshold value is also low, and the span to threshold ratio is really very high. And if you are going to other sensing material like say inductive material, we know that the strain sensitivity is low, even the threshold value is also low, and the span to threshold ratio is almost normal. They are almost insensitive to this part. And capacitive based sensing material, they have also, you see, the strain sensitivity is very low, which is by that way we cannot even make our sensors based on these features. Their threshold value is also low, and the span to threshold ratio, the entire ratio part, is also very low. So if we compare these like the basic characteristics of these material, then we will find that as far as the vibration control is concerned, the piezoelectric materials are just showing an excellent properties which is being required in the control feature from these material. So working with these conventional electronics, we can say that not the perfect insulating material, a reduction in the internal sensor resistance will result in the constant loss of electrons and yielding an inaccurate signals. So elevated temperature also, when the temperature rises there, causes an additional drop in internal resistances, and so a higher temperature only piezoelectric material can be used to maintain the high level of internal resistances. So we know that when we are just using of such kind of material, a continuous loss of electrons are there, and then we can say that the resistance which is being coming out, the internal resistance, is very low from these things, and then there is a clear inaccurate feature in the signals are there which we can get. So that is why you see here the piezoelectric materials are one of the good materials which can be used at these places where the elevated temperature features are there. So when we are talking about vibration control, we know that we can use this material as the transducer. So piezoelectric transducers have a wide utilization in their specific application, and can be attributed to their excellent actuation and the sensing abilities, which stems from their high electromechanical coupling coefficient as well as the non-intrusive nature. And because of these two features, we can straightway apply these piezoelectric transducers as the sensor and the actuators. And when we are thinking from that vibration control point of view, these transducers can be straightway bonded, or we can say even the embedded in the composite structure, so that whatever the feature is being required, it means like the sensing or actuations, immediately it can be acted towards that. And the transfer function of these systems are of very high order, and their poles are very lightly damped. So the control problems associated with these systems are thereby no means trivial. And one of the important thing is that the piezoelectric shunt damping is very popular, as we already discussed about the shunt damping, because you see, whenever we just want to suppress the vibration for a flexible structure, we need to go with shunt damping, and the piezoelectric based material which provide the shunt damping is one of the popular part in suppression of vibration for a flexible structure. And in this technique, you see here, we can simply characterize by the connection of this electrical impedance to structurally bonded piezoelectric transducers. So we need to check it out, the impedance feature and the mobility of these, of this structure. And such methods do not require an external sensor. If we design these things, they can certainly give a proper stability of the entire shunted system. So that is the unique feature of these, like the piezoelectric shunt damping, in which we can straightway get the stability and actuation and sensing feature from this piezoelectric part. So, single mode damping can also be applied to reduce the vibration of several several structural modes within the use of many with the use of like we can say the many piezoelectric transducers and the damping circuits. But in many cases you see here, this is not the practical solution sometimes, because you see whatever the modes are coming on the entire feature of the large system, we need to just check it out that what the variations are there. So, as far as the practical solutions are concerned, when the large number of transducers will be requiring for larger number of modes, then certainly it is not a feasible solution. And that is why you see here, when we are keeping various piezoelectric transducers and the damping circuits, they may not give the accurate result as well in the single mode damping. So, we can simply go just to develop a multiple mode shunt damping circuits, which can be used just one piezoelectric transducer and can be gauge the entire modes and suppress the vibrations. So, instead of going with the single mode damping with lots of the transducers and the damping circuit, we can straightway use, and many of the researchers they have suggested the various things that we can use the multiple mode shunt damping with piezoelectric transducers, and through that you see here we can effectively control the vibration in entire mode shapes. So, these transducers which are being acted as a sensor or like we can say actuator, just we need to see what kind of applications are there, because you see here these transducers are simply bonded to the flexible structure and can be utilized either as the sensor or actuate or sensor to monitor the structural vibration, or actuator to add the damping to the structure. So, this is the beauty of this piezoelectric device, that if we want like the sensing feature just to monitor the movement, whatever the structural movement are there, they can provide the significant information. And if we want them to act as a structure, as an actuator to the structure, they can certainly provide through their reactive forces. This kind of damping is to be provided to the system. Now, if you are going to the basic principle of piezoelectric part, then we know that the piezoelectric sensor rely on the piezoelectric effect, which was discovered by the Curie brothers in the 19th century. So, you see here, when we just investing a number of naturally occurred material as discussed, the quartz part, or we can say like the tourmaline, they have, you see, these materials have the ability to transfer the energy even from mechanical input to electrical output, or electrical input to mechanical output. So, this is what the principle which was discovered by the Curies, and those charges which are highly proportional to the applied pressure, the piezoelectricity has a linear propagation towards that. The quartz which we are talking about, the naturally shown in that there are two main elements, the silicon oxide, and the like we can say it is a tetrahedron feature is there in that. So, when the force is applied to the tetrahedron, or we can say like somewhat more macroscopic crystal element which we are going to show, a displacement of the cation charge towards the center of the anion charges are being occurred, and because of these like the transformation, the strain is being occurred in this, and because of that you see like the voltage drop, the voltage changes are there. So, the outer face of such piezoelectric element gets charged under this pressure, and you see we can simply measure the voltage difference in that. So, you can see on your screen that whenever the force, either the compression, either like we can say tension or the bending, whatever the force is being applied there, the reactive features, because the strain features are there, this is the mechanical force, mechanical input is there, the reactive features are being just changed according to the voltage drop at the outside. So, this is you see like the arrangement of the silicon and oxide features are there SiO2, and accordingly you see here the proper actions from the mechanical input to electrical output, or from electrical input to mechanical output can be occurred simultaneously. So, depending on the way of piezoelectric material is cut, the three types of operation can be formed. One, the transversal, means what exactly the action is there of the force, the longitudinal, and the shearing part. So when we are saying that you see, like we have a naturally or the man-made occurred of this piezoelectric part, a gallium phosphate crystal which we are going to show with the typical sensor element can be manufactured with these cuts, and depending on the design of the sensor with the different modes which I discussed previously, to load the crystal can be used as the transversal, longitudinal or shear according to the direction of the forces applied, and the charges are straightway generating on both sides of x-axis element, and the positive charge on the front side are accompanied by the negative charges on the back side. So there is a clear voltage changes are there when these mechanical inputs are being provided in any of the direction, transverse, longitudinal or the shear part. So you can see that we have this the gallium phosphate crystal, which is we are saying that the piezo crystal part. In this you see here, when the transverse directions forces are there, you see along the axis, the transverse part, the one axial part. So we know that you see this like the positive charge which is being followed by the negative charges are being you see like generated in that. Even if we have the longitudinal feature, like you see this is what the longitudinal part, when the forces are being just there along these longitudinal directions, then also you see the charges are being generated, and when the shearing action is there along the plane parallel, you see not along one axis but along the plane, then also you see here the charges are being generated, and we can get you see the voltage change at the outside surface. So what exactly the mechanism is working when such kind of forces are being applied to the system? The first is the transverse force with the transverse effect. So the force when they are being applied along the neutral axis, like the entire neutral axis you see here, the charges are generated along that particular direction which we are saying that D11, where the applied force and the generation means the entire plane where these forces are being naturally occurred is in the same direction, and the amount of charge is absolutely depending on the geometrical dimension of the piezoelectric element. So if we are saying that these dimensions are say like A, B, whatever, we can say that the total geometry on that you see which is being like whatever the amount of charges are being generated. So charge Cy in the y direction when the forces are being applied in the x direction is nothing but equals to minus D11, that is nothing but D11 is my the piezoelectric coefficient is uniform in 1 direction. So minus D11 into Fy is the force which is being there in the y direction into B by A, where A is the dimension in line with the neutral axis and B is the just the dimension is in the line with the charge generating. So here we can say that when you have both the things together, means when the neutral axis and the charge generation, when both are just lying in the one plane, we can say that the piezoelectric coefficients are just D11, where we can say it is nothing but the pico C by N, because it is just along one neutral axis. And if we are not going with this, and if we are going with the longitudinal effect, then the amount of charges produced, the Cx we can say now, is strictly proportional to the applied force, which is absolutely independent of the size and shape of the piezoelectric element, because now they are absolutely like going along this direction and my neutral axis is this, and we know that when we are just trying to focus on the neutral axis, the layers of the entire fibers are well settled. So certainly whatever the piezoelectric coefficients and these neutral axis line and the charges line is to be considered separately, and since now it is absolutely independent in the longitudinal effect, these whatever the charges are being generated from the size and shape of piezoelectric element. So we can simply go with that how many number of elements are there in which we can apply these forces and we can generate this electricity. So using several elements that are mechanically in series and electrically in parallel, because the charge generations are just just perpendicular to that part, is the only way to increase the charge output when the longitudinal effect is being used. So the resulting charge say Cx is nothing but equals to d11, that is the piezoelectric coefficient, into whatever the force which is being applied in the x direction, because the charge is in the x direction Cx, and into the n, that is number of elements. So this is what you see, the amount of charges being produced when the force is being applied in the longitudinal direction is d11 Fx into n. And if you are going to the shear effect, in this also the charges produced are straightway proportional to the applied force, because now this is the shearing action is being there across the fibers and are independent of the element size and the shape, just like the longitudinal part. And here also the number of elements are supposed to be there in the series, and it is supposed to be there parallel in the electrical part with the charges. So the amount of charges produced is nothing but equals to 2 times of d11 Fx into n. So in contrast to the longitudinal and the shear effect, the transfer effect opens the possibility to fine tune sensitivity depending on the force applied and the element dimension, because this is a well structured pattern there along the neutral axis. And then you see, if we are really putting the electric charges, then we need to take the shape and size of that. But in other two, longitudinal and shear effect, we know that a kind of the effect on these elements are just independent of the size. It only requiring that how many number of elements are being arranged in the series mechanically or parallel to electrically for featured out the amount of charge, is being produced. Therefore, you see we can say the piezoelectric sensor almost exclusively used the transverse effect. Please remember, when we are just going for sensing application from the piezoelectric part, then we need to use the transverse effect, since it is possible to reproduce obtained high charge output in combination with excellent temperature behavior. And the piezoelectric material can also be used as sensor to measure the structural motion by directly attaching them to the structure. So most contemporary application of the piezoelectricity used here is the piezocrystalline ceramics. That's what we discussed about the PZT part, in which we have all three parts together, the lead, the zirconium and the titanium feature is there, which can be excellently used there. So ceramic materials can afford various advantage which we discussed, and even they can provide whatever the electric properties which are being required. And the relationship between the applied force and resultant response can also be immediately get with the using of the appropriate property of piezoelectric material, its size and shape, and the direction of the forces which is being applied, or we can say the direction where the electric fields are being generated with the we can say relative to the material axis. So this is one of the beauty part here, that when we just want to apply the relations, or we just want to apply these things in the real application, we can immediately go that what exactly the requirement is and how we can generate the amount of charge, or we can say sense the forces when the voltage drops are there. So three axes can be used to identify the directions of the piezoelectric element, and correspondingly you see here we can use the rectangular coordinate or any kind of XYZ coordinate systems are there. And these axes can be set during the polling process, which induce the piezoelectric properties of the material by applying the large DC voltage to the element up to certain period. You can see that this is what all three axes part is being there. The pressure can be applied there on the particular electrode, and when you see we are simply applying the voltage drop, or we just want to measure the voltage drop corresponding to the pressure, these things are being we can say the actuated, and corresponding voltage drop can be measured, because whatever the changes are there within the element, when you see these piezoelectric featured are being there, the entire the positive and negative charges are being separated out, and they can simply generate the voltage all across the material. And the constitutive equations for the linear piezoelectric material, when a simple we can say uniform electric field is being applied, and whatever the stresses are generated, which are almost being we can say a elastic feature, means not very large, the stress generation is there, we can straightway apply these the voltage field, and we can get the strain, as the strain J is nothing but equals to S IJE into sigma j plus d Mi into Em, where the epsilon is nothing but equals to the strain which is being there, you see, in the entire piezoelectric material. Se is nothing but the elastic compliance. Elastic compliance is nothing but it is just the inverse of the elastic modulus. So, it is elastic property, as you can see, it is s to the power e, it is just the elastic property which just shows the variation in the two main, we can say, indices I comma j as per the direction of material coordinate under the elastic deformation, which shows the linearity in the stress strain featured, into sigma j is nothing but the stresses which is being there in the entire material, plus dm. Dm is nothing but, you see, the piezoelectric strain constant, that there is a constant, you see, according to the property, into Em. Em, as you know, that is nothing but the electric field which is being applied, and this is volt per unit length. So, this is, you see, one like we can say the strain can be obtained with the using of these elastic property and the strain part and the applied voltages. And second, you see here the dm, the dm is nothing but equals to the electrical displacement, in which we can say that that is nothing but the charge per unit area. So, electrical displacement, so this is one part previously which we showed the strain, that is the mechanical part, can be compared or can be obtained using the stress and the electric field. Now, we have the electrical displacement which is nothing but equals to dm into sigma I, and we know that the d is nothing but the piezoelectric strain constant into sigma I is, you see, the stress in the ith direction, plus epsilon ik, and epsilon ik is nothing but equals to, we have, you see, what exactly the permittivity of the material, you see. The permittivity is nothing but the material property which just shows that how the material is going to react against the forces, into Ek, and Ek is nothing but, as we discussed, that it is the electric field which is being applied to the system. So, we can get either the strain, or you see here this dm, that is nothing but, you see, the when we are getting these electrical displacement of the charges, we can immediately get these two, or we can simply relate when the small, we can say, these stresses or the strain are being generated with the electric field. So, this is one equation, these two equations which are clearly showing the relations between the electric field stress and strain along with the material properties. So, when we are just using these piezoelectric features in the sensor and actuators, then we need to see that what the actuation feature is there in the elastic structure, because we know that when we are applying to the static or any dynamic approach based, then we need to see that how these are being placed, how these actions are being taken within that. So, if you are talking about the static response, then it is nothing but, you see here, the interaction between the piezoelectric element and the structure, which first to be determined, and then it is to be coupled with the constitutive relations of the piezoelectric element and the structure with their equilibrium and the compatibility equation. Because it cannot be abruptly applied there wherever you see actuations are there or the sensing features are there, and we can get the accuracy of the result. No, we need to check it out. The two things, one is the equilibrium part, the stable feature in that, and second the compatibility part, and based on these things we can simply frame the equations either in the mechanical strain or the electrical displacement of that part. And once the equivalence of the static force or moment due to actuator is obtained, then we can use the frequency independent amplitude for harmonically varying input of the system. So, this is one of, we can say, that piezoelectric the stack actuator can be used like that, and this appropriate approach can be found in the reasonable good results if you see here we are just using a relatively lightweight piezoelectric elements, in which you see here the internal resonant frequency should be very high as compared to whatever the exciting frequencies are. And most importantly, the static approach includes the disturbance forcing function which is directly affecting the piezoelectric element, and that can be that can be shown laterally, a very important this attribute for selectively control states for the structural system. So, this is one of the important feature in this, that we need to check it out, that what exactly you see the internal resonant frequencies are, and then whatever the piezoelectric elements which are being used to disturb the forcing functions have to be selectively controlled all the state of this like the structurally excited systems. So now we are using one more the stake arrangement in which the external force F is to be applied, and like we can say that some external stiffness is to be represented by adding the spring there. So two configurations are just like I am going to show in the next slide, in which the actuator is working against an external spring stiffness which is arranged in parallel with the actuator, and second, the stiffness is positioned in the series, and in both the cases for 0 voltage an external spring is in equilibrium and applied no stiffness force there itself. So this is what it is, the first part in which the piezoelectric stake actuator is working against the external stiffness which is used as a parallel. So you see here, this is what you see, the forces are being there, and parallelly when we are applying the external stiffness part, even with this actuating force, they are simply against the whatever the restoring forces are being coming out from this, and then they can make the balance of the entire feature which is there on the below side. And even you see here, this piezoelectric straight actuator can work against whatever the external stiffnesses are being there in the series formation, and they can bring the entire the structure to the 0 amplitude by applying against the force against this part. So these are the piezoelectric actuators which I am just showing by the brown part, and they are working against the spring force which is being there, the external spring we can say, and they can brought the entire system into the 0 amplitude by applying their forces in this proper direction which is showing on the diagram. So as we discussed about the piezoelectric sensing and actuating applications, we know that there are two broader categories of this according to their we can say like the material properties. We can say we can like categorize in two broader categories, the natural and man-made piezoelectric materials. If you are talking about first the natural, because they are very less and in comparison to this, and they have lots of limitations together. So naturally occurring crystals are first the beryllite. So beryllite, which is nothing but you see AlPO4, is a rare phosphate mineral, and that can be even like put a category in terms of like because it has a similar character of the quartz, so we can say it is a naturally occurred this part. Even the cane sugar, the quartz, the Rochelle salt, the topaz, or even we can say that the tourmaline group minerals, they are all coming under the naturally occurred the crystal which are showing the piezoelectric featured in that. Even we can go with the other natural materials like the bone. The dry bone can exhibit sometime a similar kind of effect like the piezoelectric properties. And like the Fukada et al. In somewhere 1984, they showed during their studies that these are not due to the apatite crystals in that, which are like we can say the centrosymmetric, but they have non-piezoelectric, but due to whatever the collagen, and collagen is simply exhibiting the polar uniaxial orientation of the molecular which dipoles in its structure and can be considered as the bioelectrate, which is a sort of dielectric material, and they can exhibit a quasi we can say permanent space charges and dipole charges. So it is somewhat here some inherent properties are there of the collagen, and these collagen is absolutely like forming these polar uniaxial orientation part, and in their this orientation whatever the molecules are there, they can sometimes show a kind of like the space charges or the dipole charges towards their formations. So potentials are though to occur when the number of collagen molecules are stressed in the same way, like displacing significant number of charges which carries from inside to the surface of the specimen. And piezoelectricity of single individual collagen fibrils was measured using the piezo responsive force microscopy, and that can be like shown that the collagen fibrils behave predominantly as the shear piezoelectric materials. So this is something like which has a clear exhibition of the piezoelectric feature when the force is being applied and the electrical outputs are there according to their action. So this piezoelectric effect can be generally thought to be act as a biological force sensor, and this effect was exploited by the research conducted in the UPenn and they simply establish the, we can say like the sustained application of the electric potential, which could be stimulate both the resorption and the growth, means which is depending on the polarity of the bone in vivo robots. So this is something you see, like which has a clear application and people are using. Further, even some of the mathematical equations can be like brought out when the long bone wave propagations are there in their hexagonal crystals, like like the 6 crystals, like we can say tendon, silk, wulk due to piezoelectric textures, enamel, or we can say dentine. These are all you see like a few of the parts there itself. And when we are going towards the man-made crystals, the second category, in which we can say that the gallium orthophosphate, means you see the GaPO4 is one of the best quartz analogic crystals. So you see here they have the same feature as the natural quartz have, and the gallium orthophosphate is just containing these kind of like all the piezoelectric featured, which can be act as a straight sensing part and the actuation features. Even langesite, which is nothing but you see having the La3Ga5SiO14, means it's especially we can say a quartz analogic crystal having all these arrangement, and they are simply exhibiting the same properties together. So when we are talking about these two piezoelectric ceramics, you can see that we have the tetragonal unit cell, which has the lead titanium. So like when we are saying that the titanium is just like occurring with the critical part, then we can say this blue part which is showing the lead, the red part is showing the oxide part, and you see in between like the centered part which you are simply showing the black is nothing but the titanium and zirconium. And when you see any force is being applied, you can see that there is a clear stressed features are there when that like that this temperature is just beyond the critical temperature of that. When it is low, then it is in these things, and when it is being stressed out because of that. So this tetragonal unit cell is clearly showing that what the interaction is there in between the lead, which is nothing but the blue, and you see here the oxide features, along with we have the titanium, so lead titanium part. So the family of ceramics with this Pervovisky or the tungsten bronze structure can also be exhibit you see the piezoelectricity. So either we are just talking about the barium titanate, which is also one of the basic ceramic the piezoelectric ceramic part, or even when we are talking about the lead this lead titanium, which was previously which I shown there, lead zirconate titanium, which is one of the basic PZT part and has excellent features, and that's why you see commercially we are using these things. Or even we can say the potassium nibonate, this KBnO3, in which you see like the lithium nibonate is there, can be straightway used, either the potassium nibonate, lithium nibonate, the sodium tungsten, all these are clearly showing the piezoelectric features. But main problem is coming in these that there is a clear effect of the lead is, and this lead like is always creating some problem. As you see here, it is more concerned with the toxicity feature. And then you see here there is a clear like because of this it's a clear restriction of the hazardous substance because of the directive regulations. So to address this, there is a lot of research being happened to make these like material in the composition of lead free piezoelectric part. And in recent time you see here somewhere in 2004, the Japanese researcher led by Yasuyoshi Shito is simply discovered one of the sodium based part, the sodium potassium nibonate, means it incorporate both the features of the sodium and potassium, and they simply like made based on the nibonate NB part, and it is like showing the same character as the PZT part is, with even the high critical temperatures. Or else even we can use the bismuth ferrite, that is you see like what the bismuth part is there with the ferrite material, they can also show a clear lead based ceramic is a replacement of that. Even the sodium nibonate can also be a replacement of the lead based ceramics. But still you see here lots of things have to be confirmed whether you see they have an environmental impact or not. So still the research is going on, but this is there. Lastly, if you are talking about the polymers, so till date you see we discussed about the ceramics. The polymer based you see here, this piezoelectric part is polyvinyl fluoride, means PVDF is a perfect you see like material which can exhibit the piezoelectric formation of crystals, and they have you see like lots of piezoelectricity featured, even almost several times greater than the quartz. And unlike ceramics, where the crystal structure of material creates the piezoelectric effect under the action of anything, you see these polymers have the intertwined long chain molecules which can attract and repel each other whenever the electric field is being applied, and they can show the mechanical strain along with that. So, this is one of the unique feature, even when we are using ceramics or polymers, they can exhibit the piezoelectric feature in that. So, in the next lecture now we are going to discuss about the active vibration control category, the piezoelectric materials, what exactly the applications are there, where we can apply these things, what exactly the different kind of like the application features are there in these piezoelectric materials. Thank you.